So, we now start on a topic which involves what is called the understanding how melting and crystallization occurs in rocks. And the diagrams that are used to understand melting and crystallization schemes, they are normally derived experimentally, but sometimes they're also derived thermodynamically if the thermodynamic parameters can be found out either experimentally or theoretically. It can be determined. These diagrams are now quite well established, and there is little ambiguity about it, but it can be very, very, very complex. But the point is, if we know the basic logic of understanding simple diagrams, those strands of logic, they don't change. They remain the same. So if you need to understand complex phase diagrams, you need to really understand at depth simple phase diagrams. And that will be my attempt to teach you as to how phase diagrams are derived, and then how to study phase diagrams for conditions of what is called crystallization, where a melt solidifies, and when a rock melts. And then we will go over to what we call the consequences of this melting. Right? Now, from whatever thermodynamic relations we have studied, we are now, I think, pretty conversant with this relationship, which is G equal to G0 plus RT ln activity. And I will change my pen because this is all nonsense. And from here we know the expanded form of this reaction, which is H0 minus T into S0 plus P into V0 plus RT ln activity. And as I told you, this zero does not mean standard state. It means pure, if the phase component is pure. And we have talked about, say for example, you have a phase phi which has two components, phase components. Say I and J, then the way to express it is the following. This is how expressions are written. If I am not writing this, that means it is understood that this is how it is. We also understand that activity I in phi can be written as x into I into phi into gamma into I into phi. We also know this relationship, where xi is the mole fraction of a component in a phase, and gamma is the activity coefficient of a component in a phase. Now, when gamma I phi is equal to 1, it's called an ideal solution. And when gamma I phi is not equal to 1, then it's called a non-ideal solution. When gamma I equal to 1, then AI is equal to xi. Otherwise, we have this relationship. Before we go, it's a little repeat, but I think it's an important repeat because I don't want to get caught in a situation where people are not understanding, and I'm saying it, especially because this is not a physical class. The other point is important, this will come up later, that activity composition relations are given by a diagram which are called AX diagrams, where this is xi phi 0 to 1 and this is activity I phi 0 to 1, and this is where gamma I phi equal to 1, and this is called ideal solutions. Or it could be a non-ideal solution, but here where limit xi phi tends to 0, gamma I phi tends to 1. I told you this before. This is what is called at extreme dilution. That means mole fraction is almost 0, even though a solution may behave non-ideally, but it could end up where gamma I is equal to 1 in a limiting case. Now, having said this, it is important to realize at this moment that Gi phi is a function of pressure, temperature, and xi phi. Or you can also write x pi and phi for multi-component systems. But Gi 0 phi is only a function of pressure and temperature. That's a very important point. That free energy of a phase component is a function of pressure, temperature, and mole fraction. But Gi 0, which is the free energy of the pure phase, mole fractions don't come into play. There is a better way to show it by what is called Gibbs-Duhem equations, but we will not go into that at the moment of time. We will try and keep things simple. Now, if we take, say for example, having said this, so this equation, we will, for my convenience and for your convenience, we will always take mole fraction, replace this by xi phi. We will always do it, or we will consider it an ideal solution. Although very few minerals behave ideally, and even though they behave ideally, it requires very high temperatures to behave ideally. This is important. So if I move, the advantage of taking mole fraction instead of activity is that I neglect the term activity coefficient, which can be very complex equations. So just to simplify the thing and to get at the logic, we can write xi phi. I am not simplifying for the heck of it, but I am trying to simplify it so that you understand the logic better. These equations can take up the whole board if I write it in the full form. I don't want to do it. I don't want to confuse you. Another thing. I have talked to you about this term, PVI. This is entropy, as you know. This is enthalpy of the phase. And this is volume. Now, normally what happens if you are not talking of very high pressures, we can sort of ignore this term. It will help us understanding it. So let us do one thing. I will just write it. For low pressure, GI phi should be equal to HI phi 0 minus TSI phi 0 plus RTLN XI phi. For pure phase, GI phi should be equal to HI phi 0 minus TSI phi 0. This term vanishes because for a pure phase, the mole fraction is equal to 1 and ln of 1 is equal to 0. So the phase vanishes. Now, this is also another important aspect. Now, you must, before I go further, in these expressions, a lot of things are taken to be simplified, which is actually not the case. If I have to write a paper and write this equation, it will not be very acceptable to the reviewer, because I have neglected what is called the heat capacity equations. I have neglected isothermal thermal expansion data. I have isothermal compressibility data. I have ignored a lot of things. But as I have said, I would like to keep my equations for understanding simple. This equation is an important equation because it shows that GI, just before I forgot, for a pure phase now, this will become 0 also, because GI pure should be equal to GI phi. Now, important thing here is, if we take this equation as written, then as you increase temperature, then G should have negative correlation with temperature. G should have negative correlation with temperature. Because if you take higher temperatures, this term magnitude becomes 0 and this remaining constant. So GI should be negatively correlated with temperature. So if you increase temperature, free energy decreases. If you make the solution impure, free energy decreases. So these are some of the basic things that you should remember. Now, say for example, let's say there are two phases, alpha equal to beta. These are two phase components. Let's say this is, let's say, alpha quartz equal to beta quartz. Now, we all know that beta quartz is the high temperature. Quartz essentially is a mineral whose composition is SiO2 and it's more or less pure phase, although it's not strictly not a pure phase, but we take it as a pure phase because the other component occurs in very, very low concentrations. So anyway, let's have this type of a reaction. So, if I now draw a graph where this is increasing temperature versus G, and let's say these are pure phases, then you will have a free energy expression for say alpha quartz, beta quartz. You will have a free energy expression for beta quartz, and you will have a free energy, say alpha quartz. This is the free energy of, I'm writing just alpha to make it simpler. This is alpha quartz, and say this one is beta quartz. Right? And so we can write G alpha is equal to H0 alpha minus T S0 alpha, and G beta is equal to H0 beta minus T S0 beta. That's the expression. And we are taking a such situation where we have either low pressure constant, or P is equal to constant, and or dP is equal to 0, maybe same. So if P is a constant, dP is equal to 0. So we have taken this situation. And the two curves intersect. So at the point of intersection here, G alpha is equal to G beta. At the point of intersection, G alpha is equal to G beta. On this side, G beta is less than G alpha, and on this side, G alpha is less than G beta. Right? So the one with the lower free energy should be stable. So at lower temperatures, you can see G alpha is lower than G beta. So the alpha would be the stable phase, whereas on this side it will be beta would be the stable phase, because G beta is less than G alpha, and at this point G alpha is equal to G beta. I will not go deeper into it. So if this happens, then the delta GR of the reaction is equal to 0 at equilibrium. Okay? Now, a small point before we wind up from here and go over to the phase diagrams. You can have a situation where temperature and G, and you can have a curve and say this is G alpha and this is G beta, which means for the observed range of temperature, the free energy of beta is always lower than the free energy of alpha. So for all practical purposes, for this temperature range, beta is going to be the stable phase, because G alpha at any temperature has a higher free energy than G alpha, so beta is always going to be stable for this temperature range. Beyond this, we don't know how things happen. Another thing I will tell you before, I'm drawing here straight lines, linear graphs, but in actuality it is not linear. These are all curvilinear, because the equation that I'm using is a very simplified form, H minus Ts, this equation that I'm using. But entropy varies as a function of temperature and pressure, and enthalpy varies as a function of temperature and pressure. So although I am taking a linear negative relationship, but essentially both are functions of temperature and pressure. So what happens in the end, these are not linear, these are curvilinear plots. But we don't go into the complications, we try and understand it simply. So in this case, G beta is and G alpha. Say for example, you can see here, if I draw another graph, and this is G gamma, then you can see that there is another complication, that both alpha and gamma are unstable relative to beta. So that they intersect here is unimportant, but the chances are that they might intersect here. So in which case, GL gamma will be stable here. I will repeat. So we showed the temperature here. G beta has a lower free energy than G alpha for the temperature range. And then I drew another equation, G gamma. And you can see between alpha and gamma, gamma has the lower free energy on this side. So gamma should be stable. Above this, beta should be stable. But this stability is irrelevant because G beta is one which is stable. So beta will be the stable relation. But if you go to another higher temperature, possibly they will intersect and you can have alpha and beta stable. So the stability field of a mineral or an assemblage of mineral is a function of temperature and pressure. In fact, a very complex function. Now, let's say all of you know, say for example, phosphorite, Mg2SiO4, and you know the mineral is phosphorite, and this phosphorite in liquid, I write this equation. Essentially, it is dealing with phosphorite in solid is equal to phosphorite in liquid. That means we are talking either of melting or crystallization. We are not sure which way we are going, but the equilibrium is represented by an equal to sign. That, okay, you have phosphorite in solid in equilibrium with phosphorite in liquid. Now, if you have written this, then there will be an equation of state. Say, for example, G, I will write the product first. G phosphorite in solid is equal to G phosphorite pure solid. Since this is a pure phase, phosphorite, right? And you will have another reaction, which is G phosphorite solid is equal to H phosphorite solid 0 plus P into V phosphorite solid into 0. Okay, we write RTLN activity of phosphorite in the solid plus RTLN activity of phosphorite in the liquid. This is what we have. Now, if we take the equilibrium, we have taken the equilibrium, then you will have delta GR of the reaction will be equal to 0, because that is what I showed you. If they are at equilibrium, then you will have delta H of the reaction minus T into del SR of the reaction plus P into del VR of the reaction plus RTLN, and if we take ideal mixing as I told you, then it will be X phosphorite in the solid divided by X phosphorite in the liquid. No, X phosphorite in the liquid. I'm sleepy in the solid. This is how the expression goes to. So delta GR, if they are in equilibrium, delta GR is equal to 0. That's what I wrote. It's delta HR, and this is delta HR. Okay, delta HR essentially, if we write it like this, then this is melting. So we can write delta HR melting, delta SR melting, and P delta VR melting, etc., etc. And then we have RT-LNX phosphorite in the liquid divided by the phosphorite in the solid. If you do that, and if we, for our argument, as you ignore this term, then we have the expression equal to RT ln X phosphorite in the liquid divided by X phosphorite in the solid, and is equal to minus delta H of melting minus T into delta S of melting, and that is the expression. We will have delta enthalpy of melting of the pure, obviously of the pure phases, melting, and delta S of the melting. Now, if it was pure phase, then the free energy change of the reaction would have been delta G melting is equal to delta H melting minus T into delta S melting, and then it would be Tm melting, or in which case this will be 0 and this will be delta H melt minus Tm into delta S melting. Have you understood? I'm writing it up and down, but it doesn't matter, you can understand. It's delta H melting minus Tm into delta S melting. And if I do that, then I can write delta Sm is equal to delta Hm divided by Tm. Have you understood? So if I now take this expression and insert it here, I will get it as minus delta Hm minus T. Now you see here, it is delta Hm by Tm. Do we understand? Now once again let me repeat. That is an important point that I would like to make here. If we have phosphorite in the solid melting to phosphorite in the liquid, phosphorite in solid means phosphorite in olivine, and I don't even know whether it's pure. So I write this equation of state for the activities. But as I told you, for looking at the reaction, it is better to replace activity by mole fraction. So I take the delta GR of the reaction at equilibrium, and I write enthalpy of melting minus T into del SR melting plus RT into ln X phosphorite in the liquid divided by the phosphorite in the solid. What is this T? This T here is the temperature of equilibrium. Equilibrium of what? Equilibrium of melting. Melting of what? Phosphorite in solid to phosphorite in liquid, and I don't even know whether it's pure. That is what is called temperature, T. Now, look at this point here, this place. Now that's interesting. This is delta Gm, not Gr. This is melting of the pure phases. If you like it, you can write delta Gm 0 and delta Gm minus Tm delta Sm. This is the change in free energy between the pure phases, only pure phases. That is why this Tm is introduced and not T. So what is the difference between Tm and T? Tm is the melting temperature of the pure phase component. And what is T? It is the melting temperature of the impure component. If the impure component is pure, if had been pure, it would be the same as Tm. Now, having said this, if we go back to this expression now, if we go back to this expression, then it will be, you see here, let me write, ln x forsterite in the liquid divided by x forsterite in the solid is equal to, now I have a minus sign here, so I can take this on this side and tell del Hm divided by RT. This I do because I have taken ln, RT comes here, and I have taken delta Hm. But, because of this minus sign, this should come before. That means it will be T by Tm minus 1. Have a look at this. I have taken out this delta Hm out of the bracket here, and I have divided it by RT, which was out here. So delta Hm by RT. But because of this negative sign here, this term, if I bring it here, if I reverse this term, then it will be this term first minus delta Hm. So if I do that, then delta Hm by RT would be equal to T by Tm minus 1. Or I can write this as delta Hm by R into, now if I take the T here, it will be 1 by Tm minus 1 by T. That should be the expression. Now look here. It is an important point. I once again go back to the point that I made. You must understand it. There are two T's here. And again, I am bringing in the same point. What is Tm? Is the melting temperature of the pure phase compound at an equilibrium pressure temperature condition. And what is T here? T is the temperature of equilibrium of the phase component, not pure, of the phase component at the equilibrium Vt. So that is why you have Tm is equal to T. I hope this is clear to you. If you have questions, you can send it back, but I hope this is clear. Tm is the temperature of melting of pure forsterite into pure liquid. T is the temperature of equilibrium of melting of forsterite in the solid, which is olivine, plus forsterite component in the liquid. They are not pure. Now we come to the other term and discuss this. Now let me write it again, this little equation. So I'm erasing this, and instead, now that you have got this, so I think instead of erasing this, I will it's the same now. So I will erase this. And I will erase this. Now you see, this is a very famous equation. This is called the cryoscopic equation, if you remember. This is called the cryoscopic equation. Or it's called the equation for depression of melting point or freezing point. But there is something very interesting for you here. There are different parts of this equation that needs to be understood absolutely clearly. There should be no question of ambiguity. What? Delta Hm is the enthalpy of melting of the pure phase. R is the universal gas constant. Tm is the melting temperature of pure phosphorite. T is the melting temperature of phosphorite in an olivine. I don't know whether it's pure or impure. What is X phosphorite? X phosphorite is the mole fraction of phosphorite in the melt, L. And here X phosphorite, S, means mole fraction of phosphorite in the solid, which is olivine. So essentially we are talking of mole fraction of phosphorite in the solid and mole fraction of phosphorite in the liquid. And Tm and T. Be very clear as to what they mean. If I take pure iron and melt it, the temperature is Tm. If I put nickel into that iron and melt it, the melting temperature would vary, and that is T, without an M. Now, let us look at this equation. Before we start, we will assume thermodynamically, let's say it's easier, X phosphorite in solid equal to 1. What does this mean? We will take the case where X phosphorite in solid is equal to 1. What does it mean? It means that I am melting pure phosphorite. But it does not mean that the phosphorite is the only component of the liquid. But I am melting a pure phosphorite. Pure phosphorite with no impurities. That's what X phosphorite in the solid equal to 1 means. But that means for this condition, ln X phosphorite in the liquid is equal to delta Hm by R into 1 by Tm minus 1 by T. Now you see here, this can also be written as T minus Tm by T into Tm. Always remember this. The one in the bracket, third bracket, can also be written like this. Now you say, if T is equal to Tm, if T is equal to Tm, have you understood? What is Tm? Tm is the temperature of melting of the pure phosphorite. What is T? Melting of the phosphorite in the liquid could be an impure solid, although we have taken it now as X phosphorite. Now, if Tm is equal to T, then this term is equal to 0. Yes or no? If this term is equal to 0, then this whole term is equal to 0. Then X phosphorite will be equal to what? Equal to e to the power 0, which means 1. Tell me, have you understood? If T is equal to Tm, then this term in the third bracket is equal to 0, which means this whole term is equal to 0. That means we come to the situation that X phosphorite liquid, if you take the logarithmic out, it should be e to the power 0, and that should be equal to 1. So, if you are melting pure phosphorite in the solid, you will get pure phosphorite in the liquid, but the condition is T is equal to Tm. There is no distinction between the T's. There is no distinction between the T's. That is very, very important to realize, that there is no distinction between the T's. T minus Tm is equal to 0, third bracket 0, this right hand equation 0, e to the power 0 is equal to 1, X phosphorite is a liquid. So if you melt X phosphorite solid equal to 1, and if you have Tm is equal to T, then your X phosphorite in the liquid is also equal to 1. So pure phosphorite melts into pure phosphorite in the solid melts to pure phosphorite in the liquid. Okay, we go a different way. I'm sure you've understood this. Now you please get this very points, very subtle points, but it will become very important when we go to phase diagrams. It will become very complicated. The representation of a thermodynamics in the phase diagram is the key. Understanding phase diagram will be always dependent on the thermodynamics of it. So if you understand phase diagram in a very qualitative way, non-quantitative way, that means you have not got the thermodynamics right. Okay. So in other words, if X phosphorite in the solid is equal to 1. Now, if we take X phosphorite in the liquid equal to 1, which means pure phosphorite melts into pure liquid, that's when we write X phosphorite liquid is equal to 1. ln of 1 is equal to 0. Now this term is not 0. So 1 by Tm should be equal to 1 by T. You're back to the logic that T is equal to Tm. Now let's say X phosphorite in the liquid is less than 1. It cannot be more than 1. Mole fraction cannot be more than 1. It could be equal to 1 or less than 1. If X phosphorite is less than 1, that means what? That means this is negative. ln of decimal is a negative. And this is always a positive term. So what will happen? 1 by Tm minus 1 by T is negative. Have you understood? Is negative. That means what? Which is bigger, Tm or T? Which is bigger, Tm or T? If this has to be negative, then 1 by T should be more. So T should be less than Tm. So T should be less than Tm. I give you a little time. It's important to think. I go back again and tell you. I think we have no ambiguities with X phosphorite in the liquid is equal to 1. Let's say X phosphorite in the liquid is less than 1. If it is less than 1, then it's a decimal. If it's a decimal, ln of a decimal is negative. This term is always positive for melting. Then it comes to, this then has to be negative. That means 1 by Tm minus 1 by T is negative. If this is so, then T should be less than T. Yes or no? So if T is less than Tm, that means what? Think of it. Don't memorize. Take the logic. T then is not equal to Tm like here, but is less than Tm. That means, why will X phosphorite liquid be less than 1? Because something has been added. That is why X phosphorite in the liquid is less than 1. So, if you add something and make the phosphorite impure, then your temperature of equilibrium should be less than the temperature at which the pure phase melted. Have you understood? That is why it is called the depression of melting point. That means you add more impurities. That means X phosphorite liquid should become progressively more. The smaller decimal value, the magnitude of this will increase. If so, then this difference will increase even more. Have you understood it? This is a very, very important issue. That if you have this type of a situation where you have a pure phosphorite melting into an impure liquid by some reason, then the amount of the impurity in the liquid would cause a depression of the melting point. higher the addition of impurity, the magnitude of this will increase, and so will be the magnitude of this negative value will also increase. This is very, very important to realize, which means, now remember, X phosphorite is solid in this discussion. Now let's see what we are trying to do. We take temperature X phosphorite increases this way, and this is temperature, and this is where X phosphorite in the liquid is equal to 1. So at 1, that means pure phosphorite, this is Tm. Have you understood? This is phosphorite in the liquid. If it is 1, then that means you have temperature of melting of phosphorite. But if you reduce the X phosphorite value from here to here, then the temperature of equilibrium between pure phosphorite and an impure phosphorite liquid should be less than Tm. So this is how the curve will go. This is as you are decreasing X phosphorite, then the melting temperature, say if you have made the X phosphorite till here, then this is your T value. You know we were talking of 1 by Tm and 1 by T. This is the T value that you get. At another point, this is the T value that you get. But the Tm value remains the same. Above this, it is liquid. Below this, it's solid. At temperatures higher than this, as I told you, some of you, this is liquid. As at the temperature above the equilibrium temperature, you have everything liquid. And below this, you have solid plus liquid in equilibrium. We will do this later, at the moment. So I think this was an important aspect that I wanted to introduce. So if you know the thermodynamic parameters, broadly, theoretically, these thermodynamic parameters that I have drawn and the activity relations that I have drawn are highly simplified. People have spent their lifetime trying to model melt. So it's not very easy. It's fairly complicated. But what is important to realize is, theoretically then, it is possible by someone from you who could do it, that you can find out the variation in the temperature of equilibrium between a phosphorite and a liquid by changing the composition of the phosphorite. So, now let's say we have two minerals, A and B, which do not have solid solution relationships. They are, let's start with, remember, we were talking of X phosphorite solid equal to 1. That means let's start our assumption that these are pure phases. Let's say we start with the assumption that these are pure phases. Then I can draw a binary diagram where I have A and I have B, and let's say I have weight percent or weight fraction of A. That means here A equal to 1.0, here A equal to 0, and the opposite is true for B. And this is temperature, and at a particular pressure is constant. So for a pure A at X is equal to 1.0, you will have melting temperature of A, which is fixed. And for B, the other end member, not a solution end member, pure phase end member. Let's say this is the temperature of melting of B. And so for this A liquid, you will have a graph and similarly, if you take B end member and add A, you will also have a graph at this point. You draw a horizontal line. So this is the last point where A and B can be in equilibrium. Both A and B, pure A and pure B, will be in equilibrium with a liquid whose composition is this much amount of XA and this much amount of XB. Mark my words here. This much amount of XA and this much amount of XB. So A and B will be in equilibrium with a liquid which is neither pure A nor pure B. It is actually a solution between A and B, the liquid. So this is called the solidus, this is called the liquidus of A, this one, and this is called the liquidus of B. And this is the solidus. This is the solidus. No melt exists below this. So here you have only liquid, and we will come to this topic very strongly. This is liquid. Here A is in equilibrium with the liquid. Here B is in equilibrium with the liquid. Here A solid plus B solid, and there are no liquid. So that is how the diagram will look like. This is A solid plus B solid. Pure solids, remember, X phosphorite was S0 equal to pure phase. Here it is pure A plus liquid. Here it is pure B plus liquid. And here it is a liquid. So the composition varies of the liquid varies between A and B. Liquid varies between A and B. But the composition of pure A is stuck at this point, XA equal to 1.0. And for this, it's XB equal to 1.0. These are the pure minerals that will crystallize. So, once more, we have Ln. What was the expression? I have erased it. Okay. XA, yeah. Pure X in the liquid is equal to delta HM by R into 1 by Tm minus 1 by T. That was the expression. And we derived this phase diagram where L is the composition of the liquid. This is the liquidus of A. This is the liquidus of B. And below this, at this point, this is called the solidus. And this point is called the eutectic composition. These are all Latin terms. Eutectic composition. We will come to the complications of this very soon. And this one here is temperature of the eutectic. This is the eutectic temperature. Eutectic temperature. So this point is called TE, the eutectic temperature, and this point is called eutectic composition. We call it XEU, eutectic composition. And this is the eutectic temperature. So you have a melting temperature at a constant P, you have a melting temperature A, you have melting temperature of B, you have eutectic composition X, you have eutectic temperature of E, and this is your phase field liquid plus B plus liquid plus A plus liquid, and below this you have A solid and B solid, not solid solution, they're separate solid, the mechanical mixtures of pure A and pure B. Mechanical mixtures of pure A and pure B. Okay, I think I will stop here. Huh? Fine, thank you.